All right. Hello and welcome, everybody. Thanks for the introduction, Tom. As Tom said, I'm going to be talking about 2DX. I'm going to give an introduction to 2DX, and 2DX is an image processing software for 2D crystals, which we are going to show in more detail in the practical. Afterwards, we're also going to, IPLT is also going to be presented by Arheit Schenk, and Open Structure by Valerio Mirani. So, just having the setup in electron crystallography, we now have heard how we get our nice crystals, 2D crystals, and one would get them in a real space image or a diffraction pattern, and then we have to do some 2D image processing, usually because there are distortions in the imaging process are introduced. When you have your processed image, you get hopefully a nice unit cell, as in the processed image, and or in the processed diffraction pattern, you get more clear spots. And then you would take all your images from different tilt series that you collected, align them, and merge them into a 3D reconstruction. And this can all be done in 2DX, and this is what I'm going to show you today in a short introduction. Actually, I lied. We can only so far we can only deal with real space images, but we're working on dealing with diffraction patterns as well. So, real space images, you get you have your images from the microscope, and you will now want to process a single individual image. This is done in 2DX image. This is one part of the 2DX software. All your images merged to a 3D reconstruction will then be done in 2DX merge. And what is 2DX? What's behind 2DX? Since I'm a software developer, I like to talk about programming languages, but I won't bore you long. Just the technical specs. We use actually the beautiful MRC programs developed by Richard Henderson. Some of you might, or a lot of you might be familiar with it. And we added an additional layer to it. We added a graphical user interface to it, and this is programmed in Qt and therefore also C++, and which has the advantage that is it's multi-platform, and it incorporates or integrates in your operating system. So you have the native look and feel of your operating system. I've listed C Shell here as well, and the C Shell, we use C Shell scripts to call the MRC programs and to bundle the MRC programs to make it more easier to call these programs and to get the output data and everything else. And what I haven't said yet is it's licensed under the GNU General Public License, which means it's open source and it's freely available to all of you. And that's what my next point. This is actually, it's downloadable at 2dx.org. I'm doing now commercial, but and well, of course, open source. We'd like everybody to develop on it or play around with it. We have now on the website over 400 registered users, and 2DX has been cited, has over around 30 journal citations that it has been used in for 2D crystals. And we've now also set up a new communication channel, a mail list, where developers and users can interact. So whenever you have a problem, you can contact us, or vice versa. And you also on the website, you can comment on whatever release. And so we're really interacting with our users, and our are happy for feedback. And therefore, we also incorporated a bug tracker in the 2DX software. So you just click whenever you stumble across some error, which hopefully you won't find, and then you can enter this on our website, and we'll get right at it. It's also a feature request. So if you kind of feel that sometimes you can't do anything, or you can't process your image in the way you want to, you can do this on the website as well. And we developed installers for Mac OS X. We have a Debian package. You have the source available as well, and we're working hard on getting packages for every Linux distribution flavor. Well, at least every big distribution, and therefore change the build system to CMake. That was what I've actually been working on. So I've talked a lot about technical specs. Now I'll show you how the graphical user interface looks like. And some of you familiar with iTunes might see that it has some similarities. I won't go into details. This is actually the 2DX merge instance. What you see on the top in the central panel is all your images that you imported. You can import TIFF or MRC format, and you would then start processing. So it's not just to merge, but also to manage your data. And you would start processing on a single image by just double-clicking an image. And this will get you to 2DX image, which is actually built up the same way. I just shortly explain how the user interface is set up. So here you have the scripts, and these are paired or called the MRC programs. Yes, sorry.
So the stuff before, how do you have a stack of 70 images or 10 images? How do you get them from just a bunch of TIFF files or a bunch of converted MRC files into this? Do you have to make the folders manually, or can you?
No, you can. We'll show that in the practical. But you just go file, import images, and you can actually select all your images at once. And what we have is a dialog window as well that will parse your file names. So if you named your file names appropriate, for example, in some kind of format schema, say you entered the protein name and your tilt angle and your image number and so far and sub images, then you just can parse this as well, and it'll make these folders, as you can see here. It's actually grouped. Here are the 0-degree tilt images, here are 30-degree tilt images, and so on. So it parses this right when you import the image and makes the folders everything. And it also creates a configuration file which stores the processed information that you have. So we basically set up a database. But I will go into more detail later. Or is there? Yeah. If you're part of the practical, because I'm running out of time, right? So yeah, okay. But I still have much to say. So, okay. Let me get back to the 2DX image. This is where we do image processing, and these are the standard scripts. This is what's the main workflow. They are executed consecutively, and you can process an image automatically. You just select all the scripts and press play. It's actually running right now. That's why it has a press button. And well, here is the central panel. So let me go through this. You have different custom scripts as well, where you can do more, analyze your image more. But here in the central panel, you have your processing data, which are input and output parameters, or even just parameters giving information about each processing script. So here, this is from the initialization script. You see the image side length is about 8,000 pixels, and what you would want to enter. These are the only two parameters that you would want to enter, even if automatically, is the magnification and the pixel size on the recording medium. Otherwise, you just press play. And this is then, yeah, you do that in the control panel, and once it's running, you have the progress bar here and the script display that is actually running right now, depicted in blue here. Whatever's outputted by the script is here in the log file browser, and you even can display different verbosity levels. The resulting values come up here from every script, and here actually you have, which is probably the most interesting stuff, is the images. So like if you did your Fourier transformation, you can double-click here on the Fourier transformation, and you get a full screen browser showing your Fourier transformation, and you can edit stuff there. Well, I'll show more of that later. We have here information about the image and a status that gives you a quality value, which is a value based on the IQ values of Richard Henderson, and gives you a figure. Well, it gives you a number of how good your image actually is. So I've explained the graphical user interface. Now let's see how the image processing of a single image is done. You can basically split it down in 3 different steps, which is determine the lattice of the in Fourier. Well, we have 2D crystals which are ideally perfectly repeated. So you have a periodical structure, and you want and in Fourier space you can get this nice lattice. So you want to determine this lattice and unbend, and then I stepped once. Sorry. The next step would then be to unbend this lattice because none of the crystals are perfect. So introduced by physical distortions in the crystal, you'd have to unbend the lattice, which actually gives you then a better unit cell. And one thing that's also important is CTF correction. These are distortions introduced by the microscope, and so what we use is the contrast transfer function to correct. The first step, like I said, is determine the lattice. You would run the get lattice and tilt script in 2DX, and what it does is it takes all the spots in the Fourier transformation and calculates the paired differences between all these spots, and by a least squares method chooses the lattice that incorporates these spots the best. And if you're not happy with the lattice, this is now the Fourier transformation in the full screen viewer, and you can look at the lattice. You have here your 0, 1 and 0 and 0, 1 vector, and you can actually refine your lattice by selecting spots in the lattice, and which then by pressing here accept first lattice would try to incorporate these spots better in the lattice. And you can also, you probably don't see that, but even though you would wish to have a mono layer, but you always have underlying a second lattice. And you would want to select the second lattice as well, because it can otherwise, because in the unbending process, which I show you now, it can interfere with the first lattice. The unbending is done automatically as well, but you want to create a reference map of a perfect crystal and unbend your lattice with this perfect crystal by doing cross correlation. So you do your first reference would be doing a Fourier filtered mask by a 1 pixel diameter, and then unbend your crystal to it, unbend your lattice accordingly. This is the deformation map you would get from cross-correlation. It's elongated by the factor of 10. And these steps are actually, you can, are done in a loop. So you would do an unbending one in the first step, and then do it as well. And 2DX has these steps in there. So it does automatically 2 sets of unbending, one with a more coarse map, and then to get the more high frequency signals as well, you would do an unbending more. The CTF correction is we determined this defocus through Nico Grigoriev's CTF find algorithm in non-tilted images. You can also use a TTF correction with tilted images. And if you're, unfortunately, you don't even see the tone rings here. I should have calibrated. I'm sorry, but there are tone rings, and we found them quite nicely. But if you don't see them, if the software didn't get them right, you can still alter them manually. And these are the main steps that you use for image process for 2D image processing, and you come up with the unit cell like that. That's actually a 2x2 unit cell generated map of GlibF. Well, you know, this is a single image. The first image you saw before? This one. Well, it's a schema, but I'm pretty sure I actually used the source. Well, it's also, well, here you don't see anything. No, not yet. We'll get to that later. Well, I induce symmetry as well, I must say, and we, yeah. I'll show. We'll go into more detail in the practical.
But you don't have the same amount of proteins in both cases. The first image is the magnification is on the same one here. That's why you see it better.
So it's clear you have 10,000 unit cells which are now.
Yeah. That's what. Oh, yeah. That was your question. Oh, I'm sorry. Yeah, of course. I mean, that's the whole point in electron crystallography, right? You have, well, that's averaging. Okay, of course. Sorry. It's not just taking one thing or one spot of your crystal. No, of course. We generate a map. I'm sorry if I wasn't clear with that. Thanks. Okay. I got sidetracked now. So after having processed your images, you would use all the processed images and with different tilt angles as well to get a 3D reconstruction. And as I said, this is done in 2D X merge, and you've seen this before. And what you would do is in the first step, take only the non-tilted images, and now you average. But first you scale as well. You scale because all these images are taken from different crystals. So in non-tilted images, you would have to scale them appropriately and register them correctly. That would be the 2D merging step, and then you would incorporate all your images with different tilts, 30, 45, up. You can go up to 70, right? And get a 3D reconstruction. Because what you know here in Fourier space, your crystal is you have these lattice lines in your Fourier space, and with your projections, you get all these planes in Fourier space, and thereby, oh, this was a bit fast, you get a 3D reconstruction. So basically, what I'm saying is, you merge all your data set you try to find them and find the according lattice in the Fourier space for your images and then do a 3D reconstruction. And this is also, again, an iterative step. So you would go back and forth from 2DX image, from 2DX merge again. When you have your first merge map, you can use this as a synthetical reference to unbend your images again in 2D image and therefore get a better unit cell in from your images in 2D and back and forth. Okay, so to summarize what I've shown here is that 2D, what I wanted to get across is as well that 2DX is easily extendable. That's why we also use the C shell script to call the MRC programs, because I think everybody can use these read through these shell scripts and edit them as they go and incorporate their own algorithms in there. So Shenyang Zhang has shown this with her maximum likelihood script for the treatment of severely disordered crystals, and Brian Gibson, the main developer of 2DX, has also incorporated a nice has done this hybrid input-output script that deals with filling up the missing cone, and this will also someday be incorporated in 2DX. His paper is submitted. So, and what I want to get across as well is that 2DX, you shouldn't be afraid of. Well, everybody could try 2DX. It got a really smooth learning curve. So you just download it, put in your image, and play with it. But it also has, for advanced users, a complete set of tools, which can give you really great results. And like I said, again, the development is driven by the feedback of the users. So we're really willing to go into the wishes as far as we can of our user base. Then with that, I want to thank the development team of 2DX, which is Brian Gibson, Daniel Castellano, who's unfortunately already preparing the practical, Shenyang Zhang, Xian Sang, and Henning Stahlberg, of course, my boss, and who organized the workshop here as well. Then the contributions of Remco Wout and Vincent Unger as well. And of course, all these people here for sharing their knowledge with us during the development of 2DX. Thank you.
Thank you very much. So we're not going to do questions because we can ask all the questions in the practical, so we just go on to the next thing.
Okay.
And so 2DX is the main development in Henning's lab for image processing. At the same time, in Andreas Enger's lab, IPLT was developed. And so in the moment, I think it's mostly useful for diffraction, right? So this is now when I introduce the practical on processing electron diffraction power.
Okay, good, welcome. So I'm going to give an introduction on the IPLT, Image Processing Library Toolbox. There will be another talk on Thursday morning, which goes more into the details of the diffraction processing. That's more now a general introduction to IPLT. So the essentials of this talk will be how we designed the IPLT framework to facilitate the novel methods development in 2D electron crystallography, and how IPLT has been used to implement new methods and also established methods. And the third part is, very recently, IPLT, a part of IPLT was integrated into the open structure framework because there were a lot of parallels, so I will also quickly talk about that. And perhaps Valeria will tell a little bit more about that part. So that's the three hats we wear if we do software development. In the beginning, when Andreas came with the idea, yeah, we should implement a new software, we were more on the left side here, the software engineering side, designing a new architecture, choosing language, choosing a framework skeleton, and also see which low-level libraries that are already present we can use. And then also one of the goals was to basically get in the end a software that is multi-platform so that everybody can run it. And then as the development went on, we went more and more towards the right side, doing methods development, so basically re-evaluate all the old algorithms and see which ones we can use, then re-implement them in a clean way. And for the ones where we thought, okay, there is some room for improvement, also provide new implementations. And also provide a testing environment to really be able to test these different algorithms to see if they're really better. Now, during my time in Tom's lab, I moved more and more to the right side, basically from the methods development to more to the structural biology side, and really also collect data and verify that the whole system works for experimental data. So these were the original goals we had. As I said, redesign the software to make it user-friendly, to have a solid base on which you can develop and extend, and also to have in the end a software which is really easy to use and to learn for the users. Yeah, and for this, it's not that we basically ignored all the things that were done before, but we tried to take the good things and implement it in a clean way in our new software, and also try to tweak them and get them easier to use. And on the other hand, also try new paths and try to see if perhaps with novel methods we can get more out of our data. And the final goal is still to actually solve all the structures, not just code. Okay. So to encourage development of new methodology, we really implemented a class-based library which provides all the fundamentals to load images, to modify images, to get all the information for images. We also had this very much modular that you basically have one part one part of the software is responsible for loading the image, and there is another part responsible actually for processing. So the processing part doesn't need to worry about how to load your images. So it's really, for a new user or for a new developer, it's quite easy to just work at one side and just implement this very small part he is interested in. He doesn't have to care about all the rest. He can just plug it in. So to be able to do that, to provide a more attractive next generation software, we decided to use C++. It's the same language as 2DX is also done in, because it allows us to easily encapsulate the different parts of the software. And also it's easy to get it cross-platform compatible so that you can run on Linux, OS X, and in the end perhaps also on Microsoft Windows. That's still a little bit an issue there. Yeah. And we also wanted to basically solve the important problems that the community has. So we tried to tailor it to the problems that were around. So one thing is it can read a lot of different image formats. So you don't have to care about how do I get my image I recorded at the microscope to the proper format to use it in the software. The software should take care of that. You can just load your image in whatever format you have. And the other thing is it's not that much true for diffraction patterns, but for images you scan from a negative, they're often huge. They can be 10,000 by 12,000 pixels. So the software needs to be able to really also process these. And basically the limitation in IFLT is how much memory your computer has. So if you have enough memory, you can, without any problem, open huge images. The third thing is we felt that it's important to have some standardized logging, that you have a format that might also be readable by other software. So we decided to basically base our input parameters for processing, but also the important results to base it on XML, to have an XML file, that's easily readable by software, but it's also, if the user wants, you can just open in a text editor and read it as a text file. So in a way, it's a little bit a compromise that you don't need a software to use it, but it's also easily usable by software. Okay, then come to the second part. So what we did in IPLT, what we implemented, how we now moved part of it to the open structure framework. So that's a crude image of how the IPLT software is built up. So at the very basic, basis on third-party libraries, some standard libraries like Qt, and there are all for Fourier transforms, for all mathematical stuff. And on top of that, we have our own layer of C++. So we use there C++ because it's very fast. It's a compiled language, so you can do the processing at quite high speed. But it's not that flexible if a user wants to add something. So that's the reason we have a second layer on top of it. So everything that's down here in the C++ layer is also exported to Python. And Python is a scripting language which is easy learnable for a new user, and it's also there. It's really easy to extend the IPLT software if a user wants to add his own module. And originally we had the full all the modules we needed in IPLT itself, but now recently basically with the implementation of the open structure framework, we saw there are a lot of parallels, so a lot of these modules are also used there. And so we decided, instead of always copying the code and maintaining 2 copies, we decided to basically put all this yellow part here into the open structure, so that people doing the open structure will maintain it, and just keep the rest in IPLT itself. Just makes maintenance of the IPLT easier, because currently it's mostly me developing on the IPLT. Yeah, so there's, well, coming to the next slide, we go a little bit in detail. There are different modules. Every module has this defined set of functions. So these are the yellow modules now. So basically the modules we moved now to open structure. There's a geometry library which deals with all the 2D, 3D, 4D vector math and matrix math. So everything is for the math is encapsulated there. There is this info layer. This we use to read the parameters from XML file and to store it again to XML file. There is the IO library, which reads most of the common image formats. So TIFF, the MRC, the CCP4, digital micrograph, but also, for example, JPK, which is used for AFMs, or Citus, which is used for modeling. So, or also the Spider, which is used in single particle. So, guess whatever format you have, chances are good that if it's a format that is often used for electron microscopy, chances are good that IPLT can read it actually. Yeah, and it's also, what is also ultimately handled is the endianness. It's a small thing, but it can be quite annoying if you switch between different machines. If you have SGI machines, if you have Linux machines, if you have Mac machines, just the order on how the data is saved is different, but IPLT takes care of that automatically. So that's one thing less the user has to worry about. And then there is a basic image module, which encapsulates the image. So the image state, the image can either be a real or a complex image, can be in real space or in Fourier space. That's all encapsulated in that module. And there is orthogonal to it is an algorithm concept. So the algorithms are not implemented directly in the image object, but are different separate classes and objects. So it makes it much more easier to implement a new algorithm, because you don't have to care about all the image stuff. So you really just have to care about this small thing, what your algorithm does to the image. Yeah. So there are various of standard algorithms implemented. Yeah, like profile filtering, convolution, correlation, and a plethora of filters and masks and searches. Then there's a second set of modules now. These are dedicated for IPLT. These are basically all the algorithms and all the stuff that is more related to crystallography. All the other stuff was more related to general image processing. So, for example, there are classes for lattice or for defining the tilt geometry or the unit cell of your protein. There is a powerful reflection functionality, so IPLT can read and write the CCP4 empty set files directly. This makes it very easy to, once you have your complete data set, to move on to molecular replacement. You can directly just take the data out of IPLT. You don't have to do any conversion. There's also now a GUI component where you can do some interactive lattice fitting if the automatic one doesn't work, or you could also do CTF fitting and things like that. There are a lot of algorithms which we use for the diffraction processing, so peak integration, binning for the scaling afterwards, or that you can mask part of your crystal. And there is a proc module that's a little bit of everything. That's basically everything that doesn't fit anywhere else. So there are the high-level scripts and high-level plotting routines. Yeah, but you will see more of these then in the tutorials and also in the talk I give on Thursday. So IPLT itself has two main executables. There's IPLT and GIPLT. This is also one of the design concepts that we always have a command line executable. So you can do basically everything in the graphical user interface if you want to, but sometimes it's just more efficient if you do it on the command line. If you have a server with a lot of CPUs, it might be easier just to run your automatic scripts there, and then you don't need a graphical user interface. You always have the choice of either doing it in the graphical user interface or doing it on the command line. Yeah. So some of the goodies of the graphical user interface, part of it was now also included into OpenStructure because they basically use the same. So there's an interactive Python shell. So even in the graphical user interface, if you click button things, if you want to do something special, you can always go to the shell and type in commands and mix this with the graphical user interface and the processing there. There's a flexible data viewer. You will see that in the tutorial then in the afternoon. So you can easily zoom in, zoom out, do a lot of stuff, renormalize image. You will see that. There's also, because the front end is now all coded in Python, and with the Python bindings to Qt, it's now very easy to add additional buttons or additional panels where you can enter additional information if you have some special protein or need some special processing for your project. Yeah. So there's interactive lattice fitting in case the automatic one doesn't work as expected. There is, based on the matplotlib, there's powerful plotting functionality. So, and at the end of the processing, you get these lattice lines in 2D crystallography. And you can easily basically plot them and click on spots and then go basically get additional information for that spot. So it's very easy and interactive then to find your outliers and find out why perhaps processing of one image set didn't work. Yeah. And the user interface is independent from the backend, so you can use the backend without user interface if you want to, but yet it's tightly integrated. So if you want to use it, it doesn't feel like somehow glued on top. It's very tightly integrated. Yeah, let's see. That's just a very small movie on how the user interface looks like. So you can rotate your lattice, you can move around individual lattice points, you can zoom in, that's probably the next one. Yeah. You can anchor points so that they don't get moved if you move another point. So there's a lot of functionality that makes it easier basically to find the correct lattice if you have to do it manually. There is also functionality to reindex, so if you by mistake swapped A and B or things like that. So that's very easy doable then. Yeah. And now I go a little bit more to the technical side to give you an impression what is under the hood. So that's now a code example in Python. So most of the coding, most of the methods and the functions you use are actually non-abbreviated English commands. So it's quite, if you read through the code, it's quite easy to understand what's happening. So you create an image, you give the size, you center it, you randomize it, so you can apply whatever algorithm, or you can, for example, here afterwards there's a statistic algorithm which gives you the maximum, the mean, the standard deviation. What you also see is here you have the image, then you apply some algorithm. So that's really two components. It's not done in the image itself. So with this, you can very, very fast, you can script together some new programs and try out new processing and see if it works. And the second thing is, if you know C++ or in Python, it's very straightforward to move from one to the other. Because if I now move to C++, the code looks basically the same. The syntax is a little bit different, but all the concepts are exactly the same in both languages. So this means you can very fast, you can implement something in Python, and then if you see that it's not fast enough, that the algorithm doesn't run fast enough, you can easily switch it to C++ to get an additional boost in speed. Yeah. So this also means that basically people can interact and contribute at several different levels. So structural biologists can basically run the executables and give feedback there, or somebody who's interested in developing some new method for a special program, a special problem, you can go to the Python layer and do some rapid prototyping there. Or if there's really a hardcore software engineer that wants to go to the highest optimization possible, can also work on C++ level. So these layers, makes it very easy that basically you can start from the outer shell, and once you feel good with it, you can slowly moving in and do more if you want. Yeah. Now, how has IPT been used to implement established as well as novel methods? So that's basically our master plan we figured out in the lab of Andreas. So how the processing should be done. So there are two legs. So basically this leg here is for the image processing, with the Fourier filtering, then with the unbending, and in the end, the scaling, merging, discretization. And here on the right side is diffraction processing. That's now the part where we were working most, because here there is there's more of a lack of software to do that part. Here, this here is very well covered by 2DX and also by the old MRC programs. This year's there's not so much software around that is easy usable, so we thought it's important to get this done well. So for the diffraction processing, there we have the complete diffraction processing with the graphical user interface. You can also use the command line interface if you want to. And this will be in the Thursday morning, Thursday afternoon presentation, and also in the tutorials you will see much more of that. We were involved in the 3D NOE of the 6th framework of the European Union. There we also developed parts here, but that's not yet the full software. So there is a proof of principle implementation of a correlation averaging, and there is a lot of internal code we used for method development, so carbon film simulation or simulation of tilted samples to see how looks basically the analog of the CTF if you tilt the sample, and how you can correct it, or how you can better unbend, and how you simulate the bends in the crystal that you can test your software. So there's quite a lot of software, but there we are still in the phase of publishing all this. But that's not yet out. Yeah, for the diffraction processing, there are basically 3 main executables. The one on top will be the one you will be using in the tutorial. So that's the graphical user interface. So that's fully graphical. You don't need to type a single line of code. You just start the user interface, then click buttons. That's basically it. And in addition, there are also these 2 command line interfaces in case there's really some hardcore guy processing large data set on server machines. That's always possible to do it on the command line if needed. But during the tutorial, we won't use these because they're a little bit more involved to use. So if you're interested in IPLT after the workshop, how do you get it? There is a copy of the software from macOS and for Linux on the memory stick you got. And there, it's also available on the website, iplt.org. It runs for majority of the Linux flavors for OS X. And now, probably it's not really a high priority to get it running on Windows, because I think most structural biologists are using Mac OS or Linux. But now that basically the main part is based on open structure, it should be quite easy to also implement it on Windows, because open structure, there they put quite a lot of effort into also getting it running on Windows. So basically, if there is the need, it should be quite easy to do, but it's not yet available for Windows. There also on the web, there are several resources. There's a wiki, and also there is a mailing list people can subscribe to. There's a user mailing list, or if people want to do something themselves, code, there's also a developer mailing list where you can subscribe. Yeah, and that's already the last slide now. I wanted to thank all the people involved, contributors, testers, collaborators. So currently it's basically me developing, and Rich is a little bit my guinea pig. So as soon as I have a new version, I give it to him to try and test it, and he gives immediate feedback if something doesn't work. I'm very happy that that I have the opportunity to work in Tom's lab. It does gives me a lot of input on the fine details of the diffraction processing and also on diffraction recording, because it's really he's the one that got the highest resolution structure of a 2D crystal. So there I get a lot of input on the small things, how you can improve it. Then I'm very grateful to the people from the Swiss Institute of Bioinformatics. It's Valerio and Marco that also worked before in Andreas' lab, and together with me developed on the IPLT, and now still help me with testing it, or help me if there are questions for the deployment things. Also, Ansgar Philipsen, he was the main developer. He's now at the Shaw, and he still gives feedback if I ask him. And there were a lot of people that actually also contributing with data sets so that we could test things out. So from Tokyo, Stockholm, Madrid, and I would like to also thank all the people now in the CGNA. Andreas Engel, he supported the IPT for a very long time. It was really his vision that we get a new software done. And also the other people that were in this lab gave useful feedback and gave data. And now we're also trying with Brian, Marcel, and Henning, trying to get together the diffraction processing and image processing, because there are a lot of projects where you perhaps not only can work with diffraction, but you also need some phases from images, or you want to use the hybrid input-output. So we're trying to get this together, that people can use both softwares in parallel, that they interface better than they do now. That's basically it. So thank you for your attention.
Okay, again, we can have questions in our practicals and so on. And so the last talk is now from Valerio on open software, you heard about. And I think, Henning, while he's setting up, we could actually organize the tutorial, the groups, the tutorials. Do people know where to go?
So forward, backward works.
So, good afternoon. I would like to talk to you today about OpenStructure, which, as Arheit Schenk already introduced, is more a library and a development environment. And you will see that it shares some common concepts and even some code with IPLT, mainly because the people who are developing it are the same people who developed IPLT before. And so they share the same vision, the two programs share the same vision and the same general philosophy. The difference is that OpenStructure is not limited, wants to not be limited only to 2D images or 3D density data that you use in electron crystallography, but span the whole spectrum of data that you use in structural biology in general. I will briefly give you an introduction, just a couple of slides, and then since time is relatively short, I will just show you a couple of things that you can do with OpenStructure, some basic data analysis, and finally, I will present Another application, in addition to IPLT, that has now been developed on top of OpenStructure, using OpenStructure as a base. So I will not spend too much time on these slides because a lot of these concepts have already been introduced by Andreas. So like he showed, we have a C++ core, which is optimized for speed and memory. This has an interface, which is then exported into Python. We have different modules that can deal with different kinds of data. And like he said, we always provide a command line interface for batch processing and to run on system without displays, like clusters, and a graphical interface to do interactive work. So he already introduced some of the modules of OpenStructure and now in common with IPLT. He focused mainly on the IMG module, which is used to deal with 2D images and 3D density maps. I just would like to point out to you that there are other modules available like SEC for sequences and sequence alignments, MOL and CONOP, which deal with molecular structure and atomic models, GFX, which deals with the visualization and the rendering of 3D structures on the graphical interface, and finally, of the GUI module, which creates really the interface with which you interact with the program. So the window where you load the files, the Python console where you type the command. I will tell you about this a little bit more later. One thing which is very important for us, and I put it as a post-it here, is that in the context of OpenStructure, we're not going to reinvent the wheel. We can do a lot, but we don't want to re-implement everything. In fact, OpenStructure is designed to be expandable, and we want to use outside tools and external programs and interface with them as much as possible when they are available. So you should be ready in your script or from the graphical interface to launch this the external tool or programs and then come back to your workflow without maybe even noticing. But we're not going to redo work that has been done very well for years by other people. We have similar concepts, as you see with images, for other types of data. We have entities which represent, for example, full molecular models, like a file that you download and load from the PDB, for example. And then we have views that represent part of a structure. This can be a chemical group, like a carboxyl group, or could be something like only the side chain, only the backbone of the protein. You can create these views, these subsection, subparts of a protein in several ways, a query language, very powerful query language that you can use in your script, or even from the interactive window. You can create an object like this. And the important thing is that entity and views share the same interface. The goal is exactly the one that Andreas described before. You want to write an algorithm and only concentrate on what the algorithm does to your structure, not on what you apply it to. It should be the same for you if you apply it on the whole molecule or just a part of it. Let me give you an example. Suppose that you have an algorithm like one that we have in OpenStructure called superpose SVD, which does a superposition of two structures using single value decomposition. And now you have two structures that you downloaded from the PDB database. Now, you could apply this algorithm to both entities, and then we will get a global superposition of the two molecules. But without changing a single line in the algorithm code, you can apply it also to views. You can select two domains. You can apply the superposition on these and only superpose the two domains. And the rest of the structure follows. Now, all these tools allow you to do some quite nice and powerful analysis just by using the OpenStructure library itself and its graphical interface without developing on top of it. Let me just give you a couple of examples. One which it could be closer to something could be of interest to you. Suppose that you have the density for a loop region or for a fragment, and you build some models into it using, for example, a fragment library. And you want to visualize on the screen just so that by looking at it, you see how well the density of the models that you created would fit into the density that you have for the loop or for the fragment. In this case, you can very easily color the model according to the correlation that the density of the model would have with the densities that you have. So you see that the model that fits very well in the density is greener here, and it becomes less, a darker tone of green when the model is not so good, and almost red when it's completely out. And just to show you, the script that does this, given the data, is just here. First, I don't want to go with you throughout the script, but just to show you that in a few lines, you can really do some sophisticated representation of data. Another example, maybe a little bit more removed from the world of electron crystallography. Suppose that you have a family of protein with a domain that binds the ligand, and you want to actually verify how the residues that binds the ligand in this domain are actually more conserved than the other residues of the domain. Well, if you have a conservation score that comes from a multiple sequence alignment, you can easily create a molecular surface and map on it, so color it according to the conservation of the local residues. And then on top of this, you can have a completely different representation for the ligand itself, so an atomic model with polysticks for the ligand itself. You can show all this together. Like I said, here I show you that in red, the residues that are actually in contact with the ligand are more conserved, and the blue ones are less. And this mixes together data from sequence alignment, from a molecular surface, and from an atomic structure. And once again, the script that does this completely, not just the beam processing. If you type this into the console, or this is also an example that you can now load together with OpenStructure, you can create a representation like this in just 32 lines. If you can then, well, you can say, well, we really like your program, but we are allergic to programming. We don't want to touch Python console, not even with a poll. Well, we also have a graphical interface. This is a snapshot of the graphical interface running on macOS. And in this case, we were analyzing a trajectory from molecular dynamics. You can see several elements, the Python console here. Here, you can manipulate all the things that you see in the 3D view. And here you have a file browser. And here you have for a sequence viewer, where you can see the sequence of the protein you're visualizing. And two things I would like to tell you about this that Andy already introduced before. The first is that anything that it's available graphically, it's also available to you in the Python shell, which means you can even drag a molecule from here to here, and in the command line, will autocomplete with the object corresponding to this. And then you can run any kind of algorithm on it or do anything you want. The second, or the same, you could select several residues here, and immediately this will be highlighted here, and the other way around, of course. The second thing is that you have seen some snapshots from IPLT before, from Andreas. You see now this one from the structure. They look completely different, but the engine behind it is the same. Like Andreas said before, this whole graphical interface is built using PyQt in Python. And this means that if you develop an application for your coworkers who are not into programming and don't want to even see the console, it's extremely easy to add menu entries, to add buttons everywhere, so they don't even have to see the console. You can easily pop up dialogues asking for data if they want, and so on. Now, I would like to introduce to you another application that has been developed based on OpenStructure, which is completely removed from the field of IPLT, but just to give you an idea of the flexibility and of the power of OpenStructure as a library and development. QMean is an application that evaluates the quality of a model based on a statistical potential. What does it mean? Well, in nature, we have physical measurements that we can say, for example, a bond distance, and we have an energy associated with it. Now, if we collect a lot of structures, we'll not only see structures with the bond at the distance corresponding to the low energy. We will have a population of structures, and how much each state, each distance, each bond length, for example, is populated depends, very generally speaking, on Boltzmann's law. So you will have the states with a lower energy will be more populated, and so on. Now, statistical potentials do conceptually exactly the opposite. So they say, well, if we look in the PDB, we see that the distance between N and O atoms, for example, usually follows the distribution. So we create, through a concept that I put into quotes as inverse Boltzmann's law, a pseudo-energy profile. Now, the nice thing about this is that, of course, since this is not a term in a physical force field, it could be anything, even things that don't really correspond to a physical entity. For example, you can create an energy, a pseudo-energy profile for structural information or for structural conservation. And that's exactly what Q-means does, together with information observation potential on the interaction potential of different atoms in the structure, and together with things that really correspond to physically measurable things like torsion angles, for example. Now, if we use this potential and we evaluate the structure in the PDB, actually in a clean-up version of the PDB, we see that they have a very nice constant energy in this potential. This is except for the smallest one, because like I said, we need to count how these states are populated. And when the molecule is too small, we don't have enough things that we can count. We don't have enough torsion angles. We don't have enough bonds that we can measure, and so on. But after a certain point, we have a very nice energy term that describes the average stability of a structure in the protein data bank. As you can see, for example, this, if you see an energy profile, you can see that most of the structure cluster around a single value of the energy. So the idea now is saying, okay, if the PDB is a good sampling of the conformations the protein have in nature. So if something diverges really a lot from it, probably there could be something wrong with the model. For example, if we take this structure that has been solved by Murphy, and we apply the Q-mean potential to it, we can see that actually falls at a much lower stability than the average stability of the PDB structure. Actually, several standard deviations away from the average energy. Just a second. Well, it was, let's say, declared as solved by X-ray crystallography. But what I would like to show is that it sounds fishy that it's so less stable than the one in general in the PDB-Phi. And actually, this structure was retracted. And the author has been investigated for scientific misconduct. So just to show you that the Q-mean could actually show that this structure was basically made up and not even very well, if it could be detected like this. Yes, that's a danger, of course, as always, that people who do scientific misconduct become smarter and smarter. But actually, there were several structures by this guy in the PDBs that turned out to be most likely, I mean, it has been at least doctored, it's not faked, and he became much better over time. So if you look at the structures, they become more and more stable and more PDB-like with time. So I was just to summarize what I've been showing you, that so about open structures, that it runs now on Windows, macOS, and Linux. And on Windows and macOS can be installed even without administrative rights. So you can install it, if you have the administrative rights, you can install it for all the user, but you could also install it in your directory. Like Andy showed, it has a clean C++ low-level interface, which is exported to Python almost verbatim. It can run in a non-graphical environment. In fact, we run it a lot in our cluster. But it has a user-friendly graphical interface, which is especially easy to extend. So like I said, you can create your own graphical interface for your application. The license is also LGPL, which means that you can use it for commercial programs. And if you do, you only need to share the code if you made modification to the base library, not to your application. So your application can be closed source. If you make changes to the low-level libraries, then you have to share the code. And of course, like Andy said before, it's open source, so collaboration are actually encouraged. This leads me to the acknowledgement. So currently, Marco, myself, and Jürgen are developing open structure in the lab of Torsten Schwede, my boss. Ansgar Philipsen, together with Torsten, was the initiator of the original idea of open structure. Now, as you heard, he's working at DShow, but still collaborates with us. Arheit Schenk, who is here and works in Thomas Pfalz lab, is developing mainly IPLT, and of course gives a lot of input back in general on open structure, and especially on the manipulation and management of images and density maps. And Pascal developed mainly Q-mean and Stefan is a programmer who mainly works on the graphical interface. The funding on our side comes mainly from the Swiss Institute of Bioinformatics. So thanks for your attention.
Okay, since we don't have a tutorial on this, you can ask questions. How do you fake the structures now? Any questions?